These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay, so before we do that, let's go over the key topics. I think this is a pretty difficult area. Have you guys been working on spectroscopy on your own?
Yeah.
All right. So what you're going to be doing, it sounds like, is you'll be given a few spectrums, and you're supposed to figure out the structure?
Yeah.
Yeah. All right. So have you been trying similar questions like that on your own?
Yeah, we've been working a lot on Proton NMR.
Okay. So, all right, well, in any case, so the first thing that you do on this type of problem is you calculate the degrees of unsaturation. Is that a concept you guys are familiar with?
Yeah.
Yes.
Okay,
Sir.
so you guys, do you guys know the formula for that? Is that something you have to have memorized for the test?
It's
Yeah.
2 times the number of carbons plus 2, plus the number of nitrogens, minus the number of halogens, minus the number of hydrogens, all divided by 2, correct?
Steve, can you see my screen?
I'm not looking at it just right now, but looks like, have you turned on your screen sharing? So far, I don't think I can see your screen yet. But in any case, before we work with that, let's work on my screen for a moment. So, all right, so here's our formula for degrees of unsaturation. Okay, so
I'm saying you. I'm asking.
let's say that a compound has a alkene. How would you be able to detect that from the data, the spectroscopy data? And you can go ahead and look at your tables.
You'd see a peak just above 3,000.
Okay. So, yeah. So anything else? Let me put it this way. What's the best way to detect an alkene?
Well, there's degrees of unsaturation.
So there would be a degree of unsaturation. Good. Although that doesn't necessarily have to be an
That could be a-
alkene. What else?
We'll see a band at like 1660.
That's right. Those are sometimes not that strong, and that kind of shades sometimes into the carbonyl range. But yeah, that's possible. You might see that 1660 band. That's right. Now, you guys haven't mentioned what I think is most important, which is the proton spectroscopy for the alkene. Well, we're looking. So the point is, when you're taking the test, are you going to be shown the actual spectra?
We don't know what we're going to be shown.
So, well, based on that handout you sent me, it looks like you might be shown the spectra. As you can see from there, the spectra are confusing because there's peaks all over the place. So what we have to do is try to focus on, in a sense, the most distinctive peaks. So I would focus for an alkene, especially on the proton NMR. So do you guys know where would the alkene appear in the proton NMR?
Alkenes are, let's see, I don't have the values memorized.
Yeah, you don't need to have them memorized.
I think
Go
they're
take a
like
look at the
past.
table. Go ahead and use the table like you would on the test.
Okay, cool. So alkenes are
1.7 to, or 5 to 6.
yeah. You'll see
These
like
terminal alkenes.
Okay.
yeah.
So that 5 to 6 region, I'm going to actually write that down as more 4.5 to 6 because that's a little bit more accurate for the
Okay.
proton NMR spectrum. Now, that only occurs if there's actually a hydrogen on one of the alkene carbons. If there was an alkene with no hydrogens on the alkene carbon, this wouldn't work. But this is the most distinctive. Why am I focusing on this? I think one of you also mentioned the 1.7 from the right-hand column. Do you see how that's not helpful, though? Because that could be many different things. Remember, we want to determine the type of functional group, so we want to focus on the most distinctive peaks that can only mean one thing. So if you look at that handout, you'll see that the 5 to 6 region is pretty much exclusively alkenes. So that gives you a much better sense for when you have an alkene in the compound. Now, I'm not saying you can't use the other things about IR as backup, but I just want to focus on what's most useful. How about, say, an alkyne? What would
It's
be?
like 2.5.
You can see that from the Proton NMR. That's right. But that's not going to be the most useful because there's other things in the 2.5 region, right? So how about from the IR spectroscopy? Alkynes in the IR spectroscopy tend to be around the 2000s to 2200s. So that would be the most useful because that would be more distinctive. How about benzene rings?
Oh, benzene rings. Those are like 6.5 to 8 on the NMR.
So that's very distinctive and quite useful. Is that on your handout?
Yeah, also if your
Yeah. So
degrees of unsaturation are
It's 4, yeah.
and as you guys said, there tends to be at least 4 degrees of unsaturation, which is very distinctive as well. Now, probably when you take the test, you're going to be given the molecular formula, so you'll know how much there is of each element. So let's say that there's an oxygen in the compound. What types of functional groups could an oxygen be in? What's one type of functional group that could have an oxygen?
alcohol.
Alcohol.
Or carbonyl.
Alcohol or carbonyl. So alcohol may be most important. How would we detect an alcohol from our spectroscopy data? What's the most useful signs?
There's going to be that huge broad group around 3,300.
Excellent. And this is why I was wondering if that was the only table you were getting for IR, because that IR table doesn't include the alcohol stretching. But it looks like you have it memorized anyway.
It does.
Sorry?
Are you looking at the same one as us?
Oh no, I sent him the one from our. I sent him this one. I didn't send him this one.
Oh, so maybe you got. No, so maybe the table I'm looking at is not the table you'll be using on the test. Okay.
On table 12-2, that's what we'll be given.
So what I was doing here is, I think it's important to start by making a list in your notes of the most distinctive ways to identify each functional group, in addition to what you already have in your tables. So here's what we have so far, the things that we've talked about. We were talking about alcohols, so what's a distinctive way to recognize an alcohol?
The broad band at like 3,300.
Yeah, so... Now, what do you know about how alcohols appear in Proton NMR?
They're shifted off to the side at a broad peak as well, aren't they? And they come as singlets.
Yeah, and there's no splitting from the hydrogen.
That's important. They're singlets. That's right. And what would their integration be?
Their integration?
Yeah.
1, right?
Unless there's more than one alcohol, yes. So that might seem obvious, but that's a very useful way to identify it, right? Because that's usually only one hydrogen. Good. Does your table say anything about alcohols? ROH. And otherwise, the point is that it's hard to predict where it's going to be because it could be anywhere from 2 to 5, although it's often broad. Okay, good. How about carbonyls? How could we recognize a carbonyl?
There's going to be a carbonyl stretch.
Yeah. And where will that be?
And that's going to be around above 1,500.
So they're usually
1700.
around 1,700 in the IR, and you can find the exact numbers on your table. That's a very distinctive and helpful thing to look at. What are some specific functional groups that have carbonyls in them?
Carboxylic acid.
That's right. So if we're looking at a carboxylic acid in particular, what would be a distinctive way to recognize that you've got a carboxylic acid?
you have a carbonyl and an alcohol.
So it sounds
on the
like
IR, so you see the.
okay, good. Anything else?
A singlet on the NMR,
Where?
on the alcohol bond,
Now,
from around
an
5.
alcohol is actually not the same thing as a carboxylic acid. So the hydrogen in a carboxylic acid in the proton NMR is not in the 2 to 5 region. It's actually in the 10 to 12 region. Do you see how that's very helpful and very distinctive? Because that's the only peak there. If you see something in the 10 to 12
Right.
region, you know for sure it's a carboxylic acid. Remember, we're trying to look for easy, distinctive ways to quickly identify the functional group. So proton NMR is best for a carboxylic acid because it's a surefire way to identify it. What's another type of functional group that has a carbonyl besides a carboxylic acid?
An aldehyde.
So how would we specifically recognize that we have an aldehyde rather than another carbonyl?
On an aldehyde, you're going to have a really special point on the NMR spectrum.
That's right. What would it be?
Aldehyde would be from 9 to 10.
And notice that's the only absorption in the 9 to 10 region. So that guarantees that you have an aldehyde. So that's something that, again, is especially useful for us to watch out for. Okay. It's also possible that you might see things with nitrogens, but you can look those up in your table separately if you need to. So these are a few particular functional groups, peaks that are worth especially focusing on and looking for. What else could, if something has an oxygen, what else could it be besides an alcohol or something with a carbonyl?
Something has an oxygen, and it could be something other than a carbonyl and alcohol.
There's one other functional group that has oxygens besides alcohols and carbonyls.
An ether.
An ether, that's right. Now, an ether doesn't really have any of these really distinctive peaks that are especially useful for detecting it. But one thing you can say for an ether, if you have an ether, where do you think that the hydrogens on the carbon that's connected to the oxygen should be? Those are going to be around the 2.5 to 4.5 region.
And they're going to be singlets as well, right? Because there's that
They
isn't
don't have to be
necessarily
singlets. No, it depends on whether there's anything that's next to them.
Right.
Now, lastly, let's actually. So let's say you just have a normal hydrogen. That a normal hydrogen that's on a regular alkane carbon. Where would that tend? Let's actually look at the handout. Okay, so what about normal boring hydrogens that aren't close to anything? They tend to be in this region, 0 to 1.5. These are just normal alkane carbons with nothing else interesting next to them. What about a hydrogen that's on a carbon that's attached to an electronegative element? They tend to be in this region, 2.5 to 4.5. If this notation makes sense, a hydrogen on a carbon that also has an electronegative element in the 2.5 to 4.5 region. And you can even be a little bit more precise than that. What about if you're one carbon away from the electronegative element? Well, then that tends to be in the middle here, say from 1.5 to 2.5. Now, these are not hard and fast rules, but they do frequently come up. Notice that this table here kind of summarizes a lot of the most important absorptions for proton NMR we were just talking about. So it would still be a good idea to study this a little bit. Here's the alkene region we were talking about. Here's the benzene region we were talking about, aldehyde and carboxylic acid. So even though you won't be using this on the test, this is a good little table to study. So, for example, let's say we've got.
Should we memorize this table?
Excuse me?
Would you suggest memorizing these because our test is timed, or should we be more reliant on previous ones?
So I wouldn't memorize. Well, you should probably memorize what I have written down right here. Or even if you don't memorize it, you should at least know that for alkenes, it's especially helpful to focus on the proton NMR. And for alkynes, it's especially helpful to focus on the IR. And for benzenes, it's especially helpful to focus on the proton. That is, you should be getting a feel for which spectrum has the more useful absorptions. So these things here you might want to memorize, or if you don't memorize the numbers, at least memorize to which spectrum you're looking at to look up the numbers. Because otherwise people get buried in too much information when they're looking at the spectrums. So these are things that you should be familiar with. Hopefully, if you do enough practice problems, you'll start to memorize a lot of these automatically. All right, so anyway, to finish this up here, so where would you expect, say, these hydrogens to absorb? What region in the proton NMR? And you can use the handout that I'd sent you.
Those are going to be from 2.5 to 4.5.
How about these?
Can you hear us?
I can hear you now. So how about these hydrogens? Where would these absorb?
Those are going to be 1.5 to 2.5.
Roughly speaking. And how about, say, these hydrogens?
Normal alkane hydrogens, 0 to 1.5.
Good. And also, which types of hydrogens tend to be more to the left? Primary, secondary, or tertiary? Which types of carbons?
Tertiary carbons tend to be more to the left because they're less shielded.
Could you say that again?
They're less shielded, so they'll be more to the left.
Who is more to the left?
Tertiary.
Tertiary, yeah. So in these regions, tertiary would tend to be more to the left and primary more to the right. By the way, you could do the same little exercise here if this was not an oxygen, but say it was a chlorine. If this was any electronegative element, you can do these kinds of ideas. Okay, so moving on. So let's say we have, so we can do compound 1. Now it's very important to cover up the answer for compound 1, right? These are pointless if you can see the answer. So you need to cover up the top, basically to cover up the top left of your piece of paper. I'll write down the formula, which is all that you need to know from there, C4H10O. But otherwise you need to cover up that top left so we don't see the answer. And then let's talk through how we would attack this. So the very first thing we should do here is calculate the degrees of unsaturation. So go ahead and calculate and then tell me what you get. What are your degrees of unsaturation? I think this one I'll do on my screen as a demonstration, and then the next one you can do on your screen. So you can just tell me what would you get as your degrees of unsaturation when you're ready.
Did you get 0?
Yeah, it's looking like 0. Yeah,
Yeah, we
2
got
times
0.
4.
So what does that
Plus
mean,
2
that the
minus.
degrees of unsaturation are 0?
No pi bonds,
rings.
no rings.
No pi bonds, no rings. Excellent. Okay, so what I would suggest doing next is focus on the oxygen and try to figure out what type of functional group the oxygen is. So what type of functional group do we think this oxygen is?
There's in the IR spectrum, there's the broad alcohol stretch. Is that what you call it?
Yeah, and it can't be a carbonyl since there are no pi bonds. So it would have to be an alcohol or an ether. So it's looking like an alcohol though.
Oh yeah, there's no carbons.
Yeah.
Okay, good. So it's looking like this is a alcohol group. So then we would write that part of our structure looks like this. And do you see what is this oxygen connected to? What atom is this?
It would have to be a carbon.
That's right. That's obvious, isn't it? But we may as well write that down. Since we know that's a carbon, we may as well write down that that's a carbon. And then how many other bonds does this carbon have?
So 3.
So we may as well write those down. We don't know exactly what they are yet, but we can write those down as well. Okay. Now, you might want to try to figure out which what's on this carbon. So you might want to ask yourself which of the information from the proton NMR refers to this carbon. You have 5 different peaks. So of those 5 different peaks, which of those peaks have we accounted for already?
The peak that's got 1 split.
Okay, so we've counted for this. So now we need to do, so which of those peaks do you think refers to this carbon?
Which peak refers to
the carbon that's
hydrogen
next to
carbon?
the alcohol? Say again?
which peaks on the proton
Yeah,
spectrum? Because I
that's
thought
right.
they only counted for protons. See, I'm not sure I understand your question
So
because the NMR spectrum only gives us information about protons.
It also gives you information like where the protons and when binders protons are.
So I'm looking at the proton NMR spectrum. So we know there's an alcohol group, and it's good. It's usually a good idea to try to figure out the structure by working away from the functional group. So working away from this functional group here, here's the next carbon. If there's hydrogens, there's probably some hydrogens on this carbon, and we want to know which of these peaks refers to the hydrogens on this carbon.
It's probably the
So would the alcohol group have any effect on the splitting of the hydrogens near it?
Well, as you guys said
Because
earlier,
looking at-
alcohols are not split.
this is
And since alcohols are not split, they also don't split other groups. Splitting is a reciprocal relationship. So alcohol hydrogens don't split other things. We can see from this picture this alcohol was not split, so it should not affect the other splitting. So there should be a straightforward way to determine if there's any hydrogens on this carbon, which of these peaks refers to those hydrogens. And hopefully what
Would
you'll be
be
doing
one
is
of the 3. Would it be the doublet or the?
it'd have to be another singlet because it's not getting split.
There aren't any other singlets.
now we don't know whether it's a singlet or a doublet because we don't know what there might be other hydrogens next to that carbon. Right.
Oh right.
So let me give you some help. What I was hoping to use was these ideas here.
Right.
Once you've identified the most electronegative group, it should be easy to find the hydrogens that are close to the electronegative group.
So it would be the one to the far left that has the ppm greater than 3.5.
Right. Notice how that's pretty much a sure thing, because what other reason could there possibly be to be shifted so far to the left? Right? There's no other possible reason for that hydrogen to be shifted so far to the left when there's nothing but this oxygen in here. So now looking at that peak then, that tells us how many hydrogens are on this carbon.
1.
That's right, 1 hydrogen on that carbon.
Isn't the H on the alcohol group supposed to be from 2.5 to 3? Not 2.5 to 3, 2.5 to 5.
That's correct.
And so how come the one on the far, like the one farthest to the left, isn't the alcohol group?
Well, let's see. 1 second. So actually, what your handout says that the alcohol should be between 2 and 5, right?
2 and 5. Okay, that's one.
Your handout says alcohol hydrogen should be between 2 and 5,
Right.
Yeah.
and this one is between 2 and 5. And there's no rule that says it has to be the furthest to the left. So notice that this is for this idea here is for hydrogens that are on carbons that are connected to electronegative elements. Those get pulled to the left. That doesn't mean the hydrogen that's on the electronegative element gets pulled to the left. Those are 2 different things.
Oh,
Here I have a hydrogen on a carbon
Okay.
that's connected to the electronegative element. Those get pulled to the left. Hydrogens on electronegative elements don't necessarily get pulled to the left. In fact, we can see from your table that the hydrogen on the oxygen is variable anywhere from 2 to 5. So it doesn't have to be pulled too far to the left. It's the hydrogen on the carbon that's connected to the oxygen that's going to be pulled fairly far to the left of 2.5. Does that answer your question?
Okay.
Okay.
Yes, it does.
All right.
Thanks so much.
So what I'm trying to do on this problem is kind of demonstrate a method for working this out. And the method is start by focusing on finding the functional group and then try working away from the functional group. So now working away, I know what element is this.
Carbon.
Yeah, how do you know? Because that's the only thing left. It can't be a hydrogen because remember this had an integration of 1. And how many bonds does this carbon have?
3.
So I might as well draw them in. All these little steps can help us here. What element is this?
Carbon.
Because it can't be a hydrogen, and I can draw in 3 bonds here. And I can even go a little bit further. Notice I only got 1 carbon left. So I may as well draw that carbon here. There's really no other place I can put it. I could put it here, but that would be symmetrical. And that has a bunch of bonds. And now what?
Well, you really only have hydrogens left, right? So you might as well fill them in.
So we're done, aren't we? By working away from the functional group, we were able to work out. And now you could try to confirm this against. So that's one method you could use for this problem. That's often helpful, I find, working away from the functional group. And the reason why that works here is because we know that the hydrogens that were closest to the oxygen should be pulled furthest to the left. Does that make sense how I got this picture?
Oh, yeah.
Now, that's not the only way you could do this. Something else you could have done is, so when we see that this peak here that says 3H, what does that probably represent? Let's do this again from the other direction. Let's say that we didn't know the structure.
Yeah.
What does this probably represent, this 3H?
Methyl group?
It's probably a methyl group. Now, it could be 3 CH groups, right? But that's not very likely because there's only 4 carbons in the whole compound. So it's pretty sure it's not 3 CHs, it's 1 CH3. So what does this probably represent?
Another methyl.
Pretty much it has to be another methyl group, probably.
But it's probably closer to the electronegative, just a tiny bit closer to the electronegative.
Yeah, it's not a very big difference here, but maybe it's a little bit closer to the electronegative group. And then what does this probably represent?
Let's see, a CH2 group.
Yeah, what else could it be? It could be 2 CH groups, right? But that's actually impossible here because notice there's only 4 carbons and we have 4 peaks. So we basically know each of these is a separate carbon. So we know there's a CH2 group as well. Maybe going back to this over here, this has pretty clear splitting, I think. So how many hydrogens are on the carbon that's adjacent to this?
Well, it has.
Would you call this a singlet, a doublet, or a triplet?
That's a triplet, so it's going to have 2 hydrogens on the adjacent carbon.
So in fact, now we know that this peak is on the carbon attached to this one, if you see what I'm saying. Because this is the only thing with 2 hydrogens?
Yes.
Oh.
Okay. So that's how we could use the splitting here. We know this is the CH2 group based on this splitting. And this has pretty clear splitting too. Is this a singlet, a doublet, or a triplet?
That's a
doublet.
A doublet. So how many hydrogens should be on the carbon it's attached to?
1.
1. So that must be this carbon over here, right? We know this isn't the alcohol because it's got splitting. So now we've assigned all 4 carbons. We've assigned all the carbons at this point, and now we can kind of put these together. We can say that this CH3 CH has to be connected to this CH3, and the alcohol must be here. So I just showed you kind of 2 ways to work this out. The first way, which I think should be your default, is to work away from the functional group. But you could have done this in the opposite direction and started with these methyl groups, because it's so clear they're methyl groups. Notice that this peak, the splitting isn't helpful because it's too complicated. I can't really tell whether this is a singlet or a doublet or a triplet. All I could say is this is next to a bunch of hydrogens, right? This is next to a bunch of hydrogens, but it's hard to say how many. The reason why this splitting is complicated, you can see why. It's because it's between two different types of carbons. That tends to make the splitting difficult to interpret when you're between two different types of carbons. How about this splitting? Can we tell what this splitting is? This is hard for me to see as well. It's hard to see the little peaks on the end, so the splitting here is probably too complicated to be helpful. So you have to use judgment. Here, the splitting is a clear triplet, and here it's a clear doublet. So in these two cases, the splitting was helpful. But when the splitting gets too complicated, sometimes you can't rely on it too much. Okay, so those are two different techniques that you could have used to come up with the same answer on this compound. I think it's best to start with a functional group and work away from it, using the idea that the group that's closest will be furthest to the left. But it might also help to work a little bit from the opposite direction and identify the methyl groups as well. So you kind of just have to put the pieces together. It's like a kind of a puzzle. And notice how I kept writing down everything I could at each point. Any little thing you can figure out, even if it's just the number of bonds, can be helpful. Okay, did that method make any sense for this problem?
Yes.
Yeah, okay. So now the next thing, move on to the next compound. So again, cover up the top left so that you don't see the answer. I'll write down the molecular formula here so you don't have to look at the top left. So the molecular formula is...
Should we look at the mass spectrum?
I don't find those to be too helpful. Maybe I just don't know as much about mass spectroscopy. But the mass spectrum, the most important thing that gives you is the mass. But you really don't need that since you're going to be, I think you're going to be probably given the molecular formula. If you're given the molecular formula, the mass spectrum is really not too helpful as far as I can see. But also, I just don't understand mass spectroscopy as well as the other spectroscopy. So maybe there's some useful information you can get from that I'm not familiar with. But yeah, I can't help you too much with the mass spectroscopy. I've never really gotten good at using that to solve problems. I think that the IR and the Proton NMR are usually much more helpful. If you have any techniques that work for you with the mass spectroscopy, that's great. But I've never found that to be too helpful. Okay, so here's our compound. So this one, why don't one of you work this on your screen? All right, so go ahead and try working this out now.
So it was
C4H8O.
H8O.
There's a carbonyl stretch, so we know that the O is for carbonyl.
Mm-hmm. So we have stretch.
And then this gives us the NMR spectrum gives us 3 peaks, but there are 4 carbons. So we know that one of the carbons doesn't have any H's. And it's probably the one attached to the carbonyl, because if that had 2 H's, then there wouldn't be anything left in the compound. And then it looks like we're going to have one methyl group.
And it's it's a triplet, so its adjacent carbon has 2 hydrogens on it. That's it.
So yeah, there's going to be, it's going to be attached to one CH3 group and then CH2CH3.
Yeah, the carbonyl. You have a CH3 group that's attached to CH2. So that can only be here and here.
And that also makes sense with the
and then there's another
PPM.
CH3 group that's like right close to the carbonyl because it's like really pulled to the it's pulled to the left. It's like past 2, so that methyl group can be here, and then the carbonyl group is even closer. Well, even more pulled. So that has to be adjacent to the carbonyl as well. So I think that's our final answer.
Okay. You check the splitting on the CH2 group. That's pretty clear in the spectrum. Does that match your picture?
Yeah.
The splitting in the CH2 group.
Yeah. So the CH2 group has a quartet, which means that the adjacent carbon has 3 hydrogens on it. So we have to know that CH2 is attached to methyl.
Okay, excellent. Okay, so that was a very good, expeditious way to work through that. Excellent. Just one thing to add there. So you saw there was an oxygen. How did you know it was a carbonyl?
From IR.
The IR was pretty clear because there was a 1700 peak. So what were the possible functional groups that it could be? Once you saw that it was a carbonyl, what possible functional groups could it be?
Ketone or an aldehyde.
That's it. It can't be a carboxylic acid or an amide or an ester because there aren't any other N's or O's, right? So you knew from the start it had to be either a ketone or an aldehyde. And how do we know it's not an aldehyde?
It's not an aldehyde because there's no peaks with one H on them. And if it were an aldehyde, it would need to have that.
Yeah, and the aldehyde peak is like, can I see the chart again?
Oh yeah,
I didn't get to fully copy
it's
out
real high. The aldehyde peak is 9 to 10.
That's right. So that's just one thing I would have added there. So looking at this compound, you know there's a carbonyl. So I would write down the carbonyl. And we know it's not an aldehyde because there's no 9 to 10 peak in the proton NMR. So you can start with this. So I just wanted to point out to you here, we know from the 1700 that there's a carbonyl, so we can write this down. We know that it's not an aldehyde because there's no 9 to 10 proton NMR. So we know this is a ketone, so there's a carbon on both sides. And actually, there's only one more carbon, right?
Right.
So we know this is a carbon, and now we're done. We've assigned the oxygen and all the carbons. So my point here is that actually in this case, if you see the 1700 peak and you see there's no 9 to 10 peak on the proton NMR, that is the only information you need to solve, and you have this, that's the only information you need to solve the entire structure.
Yeah, because you can just fill in the H's.
That's right. 1700 tells us there's the carbonyl. We know it's not an aldehyde, so we can write these 2 carbons, and then there must be another carbon attached to them, and the only thing that can go in all the other places is hydrogens. And now, I'm not saying you have to ignore the other information. You can confirm this is right now by checking against the proton. But you can see how much information you can squeeze out just from these 3 pieces of information. So I just wanted to point that out here. So it's very helpful to identify what the type of functional group is and then work away from the functional group. So that's just something else I wanted to point out. But you guys did a good job on that problem. That was a good, efficient way of working out the structure. I just wanted to point out how much information we could squeeze out from just these ideas. Okay, that's good.
Could you quickly just go back up to the the first thing you wrote, where you had all like the salient points of how to identify like carbonyls and all that. Right. Yeah. I just need.
You're gonna send us those.
But this would be a good thing to copy right now so you can use it during our session.
Yeah.
Yeah, so the reason I wrote this down is that hopefully this is something you guys can refer to during the session as particular things to watch out for. So that this would be a good thing to have in your notes.
Yeah, I'm just going through this really quickly. I'm sorry.
No, take your time. It's important for you guys to have this in your notes so you can use it while we're doing the problems.
And then for a ketone, you wouldn't put that it's an identifying thing that's at 2.1 because there's so many things that can be between like 2 and 5.
Well, I wouldn't put that on this particular list, but it is good to realize that if you have a ketone carbon, then what range should these hydrogens be in? They should be in the 1.5 to 2.5 region usually, right? Because they're on the carbon that's connected to the carbon with the oxygen. So they would be like these carbons here. So that's true for many different situations. And then, you can write that down if you find it helpful. I'm not putting it down here because I wanted to put the particularly helpful and distinctive regions. If you see a 1.5 to 2.5 hydrogen, that doesn't tell you you have a ketone. Whereas if you see a 9 to 10 9 to 10, that tells you for sure you have an aldehyde. So these are especially helpful to put down, but that doesn't mean we want to have amnesia about this. This is also helpful to realize once you know it's a ketone, you can usually identify the hydrogens that are closest to the carbonyl because they should be a little bit pulled to the left.
Okay.
Notice that with a ketone, you don't expect anybody in the 2.5 to 4.5 region. With a ketone, you don't expect anything in the 2.5 to 4.5 region because there's no hydrogens on this carbon.
Right.
Okay. And if there was a hydrogen, it would be all the way in the 9 to 10 region, actually. Okay.
Okay. I will go back. Thanks so much for going back.
All right. So shall we try number 3?
Okay, cool.
So again, make sure that you don't look at the top left corner. So I'll just tell you that the formula is C8H8O2, and you can, C8H8O2.
8H8O2. Two times 8 plus 2, minus 8, plus 16, plus 2 is 18 minus 8 divided by 2 is 4. No, 1. No, that's careless. No, it's 5.
Yeah, so I think there are 5 because in saturation.
Can I actually ask you? Yeah? So are we given the thing to begin with, or do we have to like work the molecular formula, or do we have to like find out through the
we'll be given the molecular formula.
We'll be given the mass spec and the molecular formula?
Yeah, we didn't learn carbon NMR, so how would we figure out the molecular formula?
I thought you gave the molecular formula for the mass spec.
I really hope.
Alright.
No, I don't think so.
I can email the other. Okay, so what else do we have? This.
No, I think he was hoping to get to carbon NMR, but then he never did.
Okay.
And without carbon NMR, the mass spec is probably pretty useless.
Okay, that's fine then. Okay, so.
It's a weird
Yeah, that's a very complicated IR spec.
It's just above 3,000 and just below 3,000. So,
Well, there's an aldehyde Wait, hold on. Is that 10? If that's 10, that's an aldehyde for sure. So we can go ahead and write that, like, in the mass spec.
Oh, there's probably also benzene ring because there's some consistency.
So,
Wait, wait, wait.
NMR at 10.
Oh yeah, there's an aldehyde, and there's
Aldehyde.
also a benzene ring.
The NMR is like just the 2 peaks of it.
So that's the H from the aldehyde. And then the one on the benzene ring, the carbon attached to the benzene ring.
Well,
5.
this is 4. So I think both these sets of carbons are on the same benzene ring, but these are going to be pulled higher because of the aldehyde group, which I think might be attached to the benzene. Right? Benzene ring has 6, yeah. And then these 3 all the way over here out 4 might be a methyl. Okay, so there's 4 hydrogens here. Carbon, H, and then the methyl group here.
The methyl group has to be pretty close to the.
Well, it's on the benzene ring, so it's going to get multi left either way. But we know they might have to be on 2 opposite sides because, like, the hydrogens are so distinctly separate. I think this is what my answer is, Steve. I don't know.
Okay.
Well, why is the methyl group? Why is that so? Why is the ppm for that so high?
Because the benzene ring
benzene
is
ring.
electron withdrawal.
Okay.
Is this right, Steve?
No.
Now, why did you decide to put the aldehyde and the methyl group opposite each other on the benzene ring? There's 2 other places you could put the methyl group, if you see what I'm saying. It could be right next to the aldehyde or 1 carbon away. How did you decide on this picture rather than some other picture?
That's not our final answer because there are 2 O's.
Yeah. The reason I put that there is because the hydrogens were so far separated, and like 2 hydrogens are equivalent. So to get each set of hydrogens equivalent, like these equivalent with A and then like these equivalent with B, you'd have to put them on opposite sides, right?
Also, the second O has to be an ether, I think, because there's no alcohol and we have no more degrees of unsaturation.
Right. No, that makes sense.
Okay.
Or you put the ether right there.
Okay.
Yeah, that might be
Great
it. Actually,
question.
no, that's
Oh yeah, it would be
good for
O
catching that.
CH3.
Which would also explain why the CH3 is so far pulled up. Final answer, Steve?
Okay, good. That was a very good process. That was a good approach. You almost lost it there at the end because you left out that oxygen. But but when you put that in, that was a good answer. So that was a good expeditious process, efficient way to attack that. You gave a good answer for how you knew where these were on the benzene ring. Okay, that's good. So again, I'm going to go back to my screen for a moment to talk about this, but you guys had a good approach on this. Can you, if you go to your Skype window, can you see my screen?
Yeah, I can see your screen.
Okay. So, so how would I attack this here? Well, first of all, the thing that jumps out at you right at the start is that there's a benzene. We should be guessing there's a benzene because there's so many degrees of unsaturation. And then we have the absorptions in the 6.5 to 8.5 region. So we know there's a benzene. And we know it's got 4 hydrogens on it. And as you said, really the only logical way for those to be arranged is like this, because we want these 2 hydrogens to be equivalent to each other and these 2 hydrogens to be equivalent to each other. Any other way of arranging it, you would get more sets of hydrogens. You need to have this type of symmetry. So that's good. You know there's an aldehyde group because of the 9 to 10 absorption. And then now the rest of it pretty much falls into our laps. We know there's a methyl group and an oxygen. So that has to be this. One thing you guys should probably be doing is we've got here CHHO2. One thing you guys might want to do is write down what you have to work with on the problem and cross things out as you go.
Mm-hmm.
That would have alerted you to the fact that you had not placed one of your oxygens. You hadn't placed an oxygen here that you hadn't noticed at the start. So you have to make sure you've actually placed all the atoms. And one thing that makes sense here now is these hydrogens are absorbing around 4. That wouldn't make sense without this oxygen. Without the oxygen, they shouldn't absorb there. If there was no oxygen here, where does your table say these hydrogens should absorb? If it's just directly connected to the benzene ring.
Maybe 1.5 to 2.5?
That's right. That's what the table I sent you would suggest.
I think it would be point.
So the table I sent you has that right here. Notice that if you have an aromatic ring and a carbon and a hydrogen, that's in the 1.5 to 2.5 region right here. We didn't talk about that before. But you can also see that on the table that your instructor is going to give you, right? That table says pH CH3 is at 2.3. Mm-hmm. If you see that. So we can see that this could, our original answer didn't make sense because it wouldn't be absorbing close to 4. So that was another clue that we really had to put in the oxygen here. Okay, so that was a good approach for attacking that problem. You did a good job with that. You just have to make sure you've actually placed all the elements. That's good. Okay, should we try number 4?
Sure.
All right, so again, make sure you cover up the top left. Go ahead and maximize your drawing window.
You can see my screen properly, right?
Let's see. Yeah, I can see your screen, so you just need to maximize your drawing window. Yeah, good. And the formula now is C5H13N. C5H13N.
So is the N, that's 1/2 of a carbon, right? So it'd be 2 times 5.5 plus 2 minus 13 all over 2.
You add the nitrogens.
What?
That's the formula. So it's 2 times 5 plus 2 plus nitrogen minus 0 halogens minus 13 hydrogens all over 2, and that's 10, 13, 13 known degrees of unsaturation.
Oh, I see. So, this is an amine because it's in the 3300 range. So we know we have an NH. If we had an amide, we'd see a carbonyl stretch, or some kind of stretch in the 1600 range. So,
That can you go to the table?
and we also know resonance saturation. So
Here, amine, amide, NH. Okay, so we have NH there.
and then this is 9H, so it's probably 3-methyl. Well, we should work away from the functional groups.
Yeah, so we'll do NH there.
Do we know if it's NH or NH2?
Thing just has NH here.
Oh, no, it's NH2.
Is that NH2?
Because there's no 1H. There's no like 1 hydrogen.
Okay, yeah, then I'll have to be NH2.
We have we have 5 carbons but 2 more peaks.
Which 2 peaks are those? That 9 looks like terbutyl. Because it's 9 equivalent, so 9 equivalent split, and it's a doublet. That looks like a doublet. So, it has. Is that doublet or triplet? Sure. That's that split.
It looks like a singlet.
Looks like a singlet. Yeah, that would make sense if it's.
It's a singlet.
Yeah.
It's not around any other carbons. That doesn't matter though. We know that, like how else would it be if it's not 3 methyl groups?
Right. So
and
then,
in order to have 3 methyl groups, you need a group. I mean, well, no. But
yeah, to get
it's
3
not
methyl groups on a
you don't know that
alone
they're all
like
the
that.
same carbon, but
But like if they're all equivalent, they should have to be in the same environment, which would mean that they're in the same
oh
carbon.
yeah, that's true.
That's a good point.
So it's gonna.
So you do that, and then that's the only thing you can do. So now we can count before I say this is my final answer.
Yeah, that's my final.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 5 thing. Okay, yeah, that's my final answer.
Okay. So looking at the Proton NMR, what type of splitting does the 9H have?
It's singlet.
It's a singlet, and does that match your picture?
Yeah.
Because the carbon that they're attached to has no hydrogens. So that's a good match. Now I see there's 2 2H signals. Which of those do you think is the hydrogens on the nitrogen?
It's going to be the ones that are more electronegative because nitrogen is somewhat electronegative.
So you're saying it's the one that's further to the left?
Yeah.
Now,
yeah, which would make sense.
That's actually a misunderstanding. Maybe I'll go back to my screen again here. So going back to my screen, it sounds like you're trying to use this idea that we were talking about here, which is that electronegative elements pull the signal to the left. But that's not when you're attached to the electronegative element. It's when you're attached to a carbon that's attached to the electronegative element. When the hydrogen is on the electronegative element, that rule doesn't apply, and you just have to look at the table to see where it is. Actually, if you look at your Proton NMR table, where does your table say that the hydrogens on a nitrogen should be absorbing?
1.5 to 4.
Which is, notice, is not very helpful. It's a pretty broad region. It doesn't have to be very far to the left, does it? So just being on a nitrogen does not pull you that far to the left. I would actually focus on something else. Which of those 2 peaks is broad?
The one on the right.
The one on the right. You see how I call it broad? It's not sharp. It's broad. That tends to be typical of an NH or an OH. That's something that isn't written there on that table, so you should just memorize that. For example, the table says that alcohols are in the 2 to 5 region, but they don't say that they're often broad. So that's something you should just memorize. They're not always broad, but often if you see a broad peak, it's probably an alcohol, or in this case, the NH. The broadness comes from hydrogen bonding. A hydrogen that's on an oxygen or a nitrogen can do hydrogen bonding. So the fact that we can do the hydrogen bonding is what can possibly make that peak broad. So then, let's see, if we look at our picture, then you ended up with...
Is it broad if it's adjacent to a nitrogen, or?
It's just profile to the left.
It has to be attached to the nitrogen.
My understanding is that the one on the left is still NH2 group because it.
I'm sorry, you just cut out for about 15 seconds. Can you repeat yourself?
The one on the right isn't. So the one on the right is not above 1.5, so it still can't be on the NH2 group, right? Oh,
that's an interesting point. Yeah. Well, I would say that it is the NH2 group. It definitely is the NH2 group. And why is it so far to the right then? I'm not sure. First of all, notice it's pretty close to 1.5. All of these ideas from the tables are not exact. So it's not too far away from 1.5. So it's we'll just have to accept it as close enough. I'm not sure why it's breaking the rule there. Maybe the table is a little bit inaccurate, or maybe this is an unusual spectrum, but this is the peak. So that's about 1.3. That is the NH group. And then this group over here is the peak that's at around 2.4. Now, this actually I would expect to be further to the left, because notice this is on a carbon that's right next to the electronegative element. I would expect that to be in the 2.5 to 4.5 region. So it's a little bit surprising, but notice it's not too far from the 2.5 region. I know for sure this can't be the 1.3. That would be far too far to the right. That's how I know this is the 2.4. And also, what about the splitting? So notice these nitrogen hydrogens don't get split. They're like alcohol hydrogens. Because of the hydrogen bonding, they don't get split. And notice, what's the splitting for this peak?
For which peak?
The 2.4 peak.
2.4 peak is a singlet.
Does that match your picture?
Yeah.
Yes, it does, because there's no hydrogens here. And remember, amine hydrogens don't do splitting. So this is adjacent to no hydrogens that can split them. So that is consistent with our picture here. Yeah, so I'm a little surprised by some of these peaks. This peak is further to the right than I would expect, and this peak is a little further to the right than I would expect. But this is still the best structure that we can come up with. So we just have to keep in mind that the rules from the tables are not always followed 100% exactly. So if you see a nitrogen, what type of functional groups are possible?
If you see nitrogen, you can have your amine, or you can have cyanide, nitrile, sorry. You can have nitrile or amine or amide. That's all it represents.
I think these are the only possibilities. And what's the easiest way here to see that we don't have a nitrile or an amide in this compound?
There's no degrees of unsaturation.
Exactly. Good. Because there's no degrees of unsaturation, we knew it had to be an amine. And that's something you guys worked out. If there were degrees of unsaturation, we might have to check for these two groups as well. Okay. All right. So I think you guys did a good job again on working that out. You interpreted the 9 H's correctly. They really do all have to be on the same carbon because they're all equivalent to each other, as you had said while you were working on that. So that's a good process. Okay. Should we look at number 5?
Okay. Yeah, we'll go on to the next one.
Okay. That's good. Yeah, practice is important for these. Okay, so again, cover up the answer on the top left, and I'll tell you the structure. Go ahead and maximize your drawing window.
Okay.
What's this?
our tools. So this is number 5. And what did you say the chemical formula was? The molecular formula, sorry?
Could you maximize your window first?
Oh, sure.
Excellent. All right, so it's C4H8O2. C4H8O2.
So no confusion on saturation.
If there's there's no reason.
Wait,
There's
hold
1
on.
degree of unsettlement.
Yeah.
So we'd have to have a carbonyl and probably an alcohol because of that, because there's an alcohol stretch. Is that an OH stretch? Doesn't look like an OH.
One degree of saturation. Easy. That's a massive OH stretch.
But it's spikes.
That might. It looks like an OH because it's broad. So yeah, it looks like we have an alcohol here. Is that a doublet?
What?
Is that a doublet?
Yeah, it's double. So it's adjacent to 1.
Yeah.
Whoa.
What was the way to tell for carboxylic acid? It can't be carboxylic acid because it's like it's not intense. I'm gonna go ahead and say that alcohol's in here. And that
Carboxylic acids have to be from 10 to 12, so we know it's not a carboxylic acid.
this 1H is a what? That's looking a little complicated. But this OH has to be attached to a C.
It's got to be, so the C has to be attached to.
So what can, let's deal with one peat at a time. So it's a 6 hydrogen peat.
There's going to be something adjacent to 1 hydrogen. And
I'm going to give you guys a hint. Here's a hint. There's something important that you guys haven't noticed in the proton NMR spectrum. Study the information that you were given about the proton NMR spectrum. There's something you just haven't noticed.
There's a
from
1
2.5
hydrogen.
from 2.5 to 3.5.
Right.
That's going to be adjacent to an OH. So you're going to have.
I think there's still something you guys aren't noticing that's very important in the proton NMR spectrum.
There's a lot of splitting. It's broad.
Yeah, it's broadly and it's split. But
take a look at what they tell you right in front of the proton NMR spectrum. In front of the box.
Oh, additional proton at 12 ppm.
Oh, really?
Thanks, guys.
Thanks. He would do that on the exam.
Oh, crap.
And then half people would notice it, and he'd be like, "Sorry."
Yeah, it was clearly there. It was in broad. It was broadly there. Yeah.
Right.
Oh,
God.
crap. All right. So.
12 ppm. What does that mean to be at 12 ppm?
12 is aldehyde, which makes sense because there's 1 degree of saturation. And
Oh no, it could be carboxylic acid.
or it could be a carboxylic acid. In fact, yeah, it has to be carboxylic acid.
Go that. Say that.
Okay, so yeah, so that's where our two O's come from then.
So then you have two, and these have to be in the same environment too.
So that's one. There's one carbon which is attached to 1H. And then these two carbons have. What am I doing?
I think I've got it.
I think about it as well.
So it'd be you'd have the carboxylic acid, and then it's attached to carbon, which is attached to an H in two methyl group.
4, 8, 2.
Yeah, that's what.
Yeah, that's it. All right. Final answer, Steve.
Okay, good. Okay, so you can see everything became much simpler once we saw that 10 to 12 peak, right? So this is a good example of how it's important to try to figure out the functional groups as early as possible. So that's just something to watch out for on the test. It looks like sometimes your instructor's spectrums don't include all the peaks. Sometimes the peaks are in the text. So better to learn that now than to learn it during the test. Do you see why he did that? Why is it in the text and not in the chart?
Because he wanted to show, kind of like when you're graphing something and you want to take off one part of the graph so that you can show clearly the rest of the graph.
Yeah, that's right. Because he'd have to shrink the scale too much to include the 12 ppm in there. If he included the 12 ppm, you wouldn't be able to see the splitting in the part of the graph that's still there. So he put it in the text because it's too far off to the left. Okay, so anyway, watch out for that on the test. Make sure that you check the text to see if there's any additional information about peaks. Also, notice, just to review, you can check your notes for this. Where do aldehyde hydrogens absorb?
From 9 to 10.
And where do carboxylic acids absorb?
10 to 12.
That's right.
So
At first, you guys weren't sure if this was an aldehyde or a carboxylic acid, but the important thing is that you checked your notes and then you saw. So you can see those are really very helpful absorptions, right? Because nothing can be in 9 to 10 except aldehydes. It guarantees it's an aldehyde. And nothing can be from 10 to 12 except a carboxylic acid. So that guarantees that it's a carboxylic acid group. You guys were hoping that the 1H in the picture was the carboxylic acid group. So that 1H is not broad. That's not what a broad peak really looks like. For one thing, broad peaks are not usually split like that. Let's look at the splitting here. What's the splitting on the 6H?
It's a doublet.
And does that match your picture?
Yes.
Yeah.
It does. That's a good thing to confirm because they're next to a carbon with one hydrogen. And what's the splitting on the 1H? Well, there's kind of too much splitting to tell. When there's so much splitting there, the splitting is not so helpful, except that you could just say it's next to a bunch of carbons. It's next to a bunch of hydrogens. So is it true that it's next to a bunch of hydrogens?
Yes.
Yeah. So we can't pay too much attention to the exact splitting there. Okay, so once you guys saw the 10 to 12 absorption, you did a good job at working out the structure there. So the key thing here is we saw how helpful that 10 to 12 absorption is. Okay, that's good. Should we try number 6?
Sure.
Yes.
All right. So the formula for number 6 is C7H14O2. C7H14O2.
What are you doing, Sharon?
Sorry.
Want to give them something?
Mhm. Looks like we have an ether as well. Because we don't have.
I start peak at 3,000 questions, so
That's probably just
okay.
alkane and stuff.
Okay.
I don't think there's anything else in that.
Well, yeah, there's peak at 714 is carbonyl.
Yeah, that's just absolutely the carbon element there. Even methyl groups from the one on the far right, on the spectrum. So we have this one on the far left with 4.
Carbon's only left with 4. That
Hydrogen.
I don't know. So let's.
So this is going to be near the ether. This is going to be adjacent to the ether.
Okay, that's fine.
Yeah.
But that would mean that the ether has to like travel a little because it's only 2H. How do you get an ether next to it?
It's 2H in the same environment of the ether. So maybe your H is like this, and then these are methyl groups or something else.
Okay, but then you'll have like. Okay.
So then these are in the same environment, but they're not in the same carbon.
Okay. Fine.
So you get that from that group. And then in the same environment, and that's a singlet. So there's 3 H's where they're not like adjacent to any of the other H's.
N equals 0.
Maybe we have
So like that's what I was saying, that maybe the well, there are a bunch of possibilities. Let's just say that there's like a methyl or 3 CHs or.
what about this one? What about this broad one with the 1H?
The broad one with the 1H. So that's just like saying that there's 1H attached to a carbon with many other hydrogens on it, but we can't tell how many because like it's so split. Let's attack the doublet though. This is a doublet, right? Yeah, so there's a 6H doublet.
Wait.
M equals 1. So you can say that there's probably this.
One of these methyl groups.
I'm going to give you guys a little bit of a hint. How do you know there's a carbonyl?
Because there's a carbonyl stretch, and then we have 1 degree of unsaturation.
Okay, good.
But the thing is,
so what I wanted to remind you of is that if you look at your IR table, the IR table actually gives you detailed information about the precise IR absorption for different types of carbonyls. And you're going to be able to use that table during the test, right? So you might want to check what exactly the table says about IR stretching frequencies for different types of carbonyls, since you'll be able to use that information during the test.
So it just says that ketones, aldehydes, acids, esters are higher, about 1735.
right.
That's 17. So it's a ketone, an aldehyde.
Well, it's not an aldehyde, it's not an acid because
So it has to be a ketone.
or an ester. It can be a ketone or an ester. Or one of the oxygens. So let's draw a ketone to start.
Well, since we have another oxygen, then let's pretend it's an ester.
Alright, let's do that then.
Oh,
Just for
that
kicks.
would no.
Yeah, okay, so if this was an ester, you drew the O there. Carbon, double bond, O. And then that's what, 4? And then like there's an alkane stretch. So So that's fine.
Or maybe this is our methyl group, the one on the other side. So the one that's on the other side of the ester, that could be this peak, the 3H at the 2 ppm.
Right.
And then,
That's what I was saying, but then we only have like 5 carbons accounted for at that point.
then we have CH3 and CH3, so that's 1, 2, 3, 4, 5. So we have 2 more carbons. So maybe
I'm gonna put the CH2 right next to the
CH2,
because it's so far
so maybe
pulled.
there's
It's pulled in.
methyl group here. So maybe there's a methyl ethyl on the C next to the O from the ether.
This is a joke. This is so
He's
tough.
gonna give us something this hard on the test.
You know what? Let's
No, I think
let's
this-
not
no,
make
this
it.
is
Let's
it.
not make it
Yeah.
a
I'm pretty sure this is.
Can I
what
see it?
Yeah. It's It makes. What I mean, I have to check, but
1, 2, 3, 4, 5, 7.
14. Like, that's it.
How do you account for that 1H? Though that 1H, that's like on its own stuff.
Crap.
Because I want to do that. What I'm gonna go ahead and say is no, don't quit the page. You know what I mean?
Yeah, I forgot about that.
I'm gonna go ahead and make it an ether and a carbonyl. So that's an O there. C.
Maybe that H instead of a methyl group right here, maybe that's an H. Yeah, that's probably what it is.
One, 2, 3, 4, 5, 6, 7. Okay, this is my final answer. See. No, that's what I thought. So what I did is I made there'd be a ketone and then an ether to burn carbons.
That makes sense.
This makes sense? Final answer, Steve.
Yeah.
I await your judgment.
Okay, so let me take a look at this.
That one's tough.
That was bad. That was not fun at all.
Okay, so let's look at the secondary carbon that's connected to the the carbon on the far. So I'm looking at the carbon that's attached to the 2 methyl groups.
Yeah, this one here. Yeah.
Wait, which one?
Which
No.
peak?
Yeah.
Which peak do you think that is in your Proton NMR?
So I think that's the one that's like pulled farther away from the CH2.
Wait,
and
that
the one
wouldn't
that
make
has
sense.
like 6. Well, it's like really, really highly split.
No, mine. That's.
Just tell me.
that-
Tell me what the chemical shift is for the height. So I'm looking at the carbon that's connected to 2
It's like
methyl
1.6.
1.6. Yeah. So that's the 1H at 1.6. It's got to be because that's the only 1H.
Right.
So does that chemical shift make sense based on your structure?
It's on a carbon that's adjacent to an oxygen, so it's going to be between 1.5. So yeah.
Okay, so let's go back to.
Well, it's 8.5 and 4.5. No, that can't make sense.
So yeah, its shifting should be between 2.5 and 4.5, right?
Yeah.
Now, remember I said those rules can be nudged a little bit, but this is way off. That's way off. Not even close. And before you erase, hold up for a second. Well, yeah, all right, that's probably good enough to eliminate that structure right there. There might be some other problems too, but that's probably good enough. So notice after you draw your picture, it's important to go back and check it against all the details. Now this takes off. So again, let's go back to the idea that we know there's a carbonyl. We know there's a carbonyl. Remember that in your table, they give you the precise absorptions for different types of carbonyls: ketones, aldehydes, esters, and amides, right? So that actually would give you a stronger clue here. So you guys were trying to figure out whether the carbonyl was a ketone or an ester, right? You guys, you needed to figure out whether it's a ketone or an ester. Well, according to your table, where do ketones absorb?
Are you looking at the same table as us?
Our
Table 12.2.
this is the IR table. We're looking at the NMR table. Oh,
Table
this is
12.2.
And by IR?
Ketones absorb above 1735.
That's not what my table says. My table says ketones are at 1710.
Oh, there's that.
Do you see what I'm looking at?
I'm gonna.
Here's the table you guys sent me.
I'm seeing dynamic. Okay, yeah, sure.
So here's the information. Yeah.
Right.
So you tell me where are ketones supposed to absorb?
Our table.
1710.
Excellent. And where are esters supposed to absorb? According to this table.
Higher, about 1735. So it's an ester.
Yeah. So and where was the absorption from our particular spectrum?
1744.
Okay, that's right. Is this the table you guys are using?
It's kind of ambiguous.
That's a better table. That's a much better
it's a good
table. But yeah.
So if you're going to be given this table, it's a huge help because it lets you distinguish between the different types of carbonyls. Otherwise, this problem becomes pretty time consuming.
I mean, I
Why
think,
did he do
no, I think if we're given this on the test, we'll lose that table. I don't think he's that bad.
Okay, so in this picture, do we have an ester or do we have an ether?
Ester.
Yeah. All right. So that's what I meant when I said we should go back and look at the table more carefully, because it can actually let us distinguish. It looks like you guys were trying to do ester and then you gave up on it. Maybe you were thinking you couldn't get it to work.
Yeah, let's try that again.
Yeah. Okay. So wrong.
I think I've got it. Maybe. 4, 5, 6.
It's 14.
I'm pretty sure it's
2. Can I see over here?
That makes sense.
1, 2, 3, 4,
No,
5.
not this, not this.
Of that.
1, 2, 3, 4, 5, 6, 7.
2, 3, Okay, yeah, alright.
So these 2H, this one is the one that's. Wait.
Alright.
No, maybe. Wait, my look. CH2 is the one that's right here.
That's what I was gonna like do.
No, but then you would have 2 methyl groups. Then you have 3 methyl groups in the same environment. So
One. So looking at this, um, alright. So
Maybe
see,
this H is in a different place. Maybe you've oh, you know what? This is probably a methyl group, not. OH.
one, two, three, four, five, six. Alright. Let's work with this one. I think this one is good. No, it can't be the one with this. Come on.
Why?
Alright, let's like
Okay, so these methyl groups are
okay, so these methyl groups are a doublet, which means that they have to be adjacent to one hydrogen only. So this works, right?
That's a
Because
good point.
they're only adjacent.
That's a good point.
where's your single H?
This H,
Oh.
this is an H over here. So I need more tough to see.
Okay.
Um,
Okay, I like that.
And then this CH2 has to be next to
The CH2 that's really electronegative.
that CH2 is a quartet. No, that CH2 is a quartet there, so it has to be next to 3, a methyl. And that's there, but this CH2 here
Mm-hmm.
is a quartet, so it has to be next to CH3. The encoding for this hydrogen and these two are really far off, which means that they're probably right next to the oxygen.
Well, this one, which I think is the one next to the oxygen.
Right.
This CH2 is a triplet, so it should be next to two other H's, but it's only next to one other H right now.
So maybe if we do this.
See, are we on the right track, kind of?
Yes. Kind of.
That's not.
No, that's not next to any. No, it's not next to any H's.
Well, there's one H that's like. Oh gosh. No, this is always next to these H's here.
Oh, yeah. Now that's C. Now you have two H's there,
Mm-hmm.
and it's a triplet, so it should be next to two more H's. So what if you take this methyl, take this CH2 group
Mm-hmm.
and put it right here? So then you have
Right
two, yeah.
So put the
Carbon
ester there. I'll put the CH2 here.
Yeah, no, so they're still in different environments. Because there's no symmetry there.
But then why would the CH3s be so far down to like 1 if they're right next to a carbon? Oh no, 1, 2. No, it's 2 carbons away actually.
What do you think? How do you now?
This is an issue.
Giving up?
Well, we don't like to put it that way.
Alright.
Is there
In fact, no,
reason for giving up?
we don't give up on
Okay.
tactical retreat.
Is that not right?
So
No, the one when he's circled. What's wrong with that?
it's wrong. It's just wrong. All right, let's just deal with the peaks one at a time. So this is the triplet. So n is equal to 2. B. That's a singlet at 3.
Okay. Yeah, I will give you a little bit of help with this. So what's wrong with the picture you have at the bottom?
A lot.
So okay. There's a high. Actually, I don't know. I think this might be right. I think the dot ch3 at the end shouldn't be at 2. That's the thing.
It should. I don't. Say again.
This ch3 here.
Yeah.
I don't think that should be at 2.
It's shifted too far to the left. You're saying.
Right.
Yeah. All right. That it is shifted too far to the left. There's something that's more definite though. So, what's the splitting on that CH3 group in the picture in the spectrum?
The ch3 group.
On the far right, what's it splitting according to the HNR spectrum? Singlet, doublet, or triplet?
It's a singlet.
And does that match your picture?
No.
All right. So those are 2 good reasons to eliminate that picture. There might be others too. Let me go to. I think if I gave you enough time, you guys might work this out. But let me give you some pointers on how to work at this a little more efficiently. So I'm going to go back to my screen. Go ahead and take a look at my screen again.
All right.
Okay. So first of all, remember we want to start by identifying the functional group. Now we know. Here's our structure, C7H14O2, and we knew there was 1 degree of unsaturation. Okay, now we know there's a carbonyl because of the 1700 range IR. So you guys were considering whether this was a ketone and an ether or an ester. So one thing we've learned is that if you're able to use that detailed table, we know it's a ester because esters are around 1735 and our peak was around 1744. So we know we have an ester group. So I would start by writing this. Let me, one moment. So going back to here, so I would start by writing the ester group. Now, what goes here?
What goes there?
Yeah.
Well, there's a peak at
What atom goes here?
Oh, what else goes there?
So on
A carbon,
your
I
chart-
guess.
It's got to be a carbon. What else could it be, right? Now, actually, there is one other possibility. For a while, you guys were considering this. This actually isn't possible, though, because notice this is kind of a combination of an aldehyde and an ester. Do you see how this is like an aldehyde ester? So this hydrogen, I think, would again be around the 9 to 10 region. If there's a hydrogen directly connected to the carbonyl, it would be like an aldehyde hydrogen, around 9 to 10. So we can eliminate that.
Is that a possible molecule? I've never seen it before.
Yeah.
I don't know. It is possible. I don't know if your instructor would give it to you. So anyway,
Okay.
but we know it. Just in case I told you that we know it's not that. We don't have that here. I just mentioned that because you actually drew that in one of the pictures you were trying out at one point. All right. So and then we have this, and what atom goes here? What type of atom goes here?
I think that's probably a CH2 because
Well, let's just
you
start with
have
it.
this.
Let's just start with the atom.
Oh, it's
We know it's a C, right? Because what else could it be? It can't be a hydrogen because then this would be a carboxylic acid. And we know it's not a carboxylic acid because there's no proton absorption in the 10 to 12 region. So I just want to point out you can write all of this down just by knowing it's an ester. Just by knowing it's an ester, you can get all of this. Okay, so this would be a good place to start. Now, what I try to recommend that you do is work away from the functional group. Work away from the functional group. So, which peaks in the proton NMR probably refer to the hydrogens on this carbon? Which peaks in the proton NMR probably refer to the hydrogens on this carbon?
the one furthest to the left because that has a 4.0 ppm and when something's that close to something that's electronegative is oxygen.
Right. Because we would predict that this would be in the 2.5 to 4.5 region, right?
Oh yeah, that's on your chart too.
We would predict that something that's on a carbon connected to an oxygen is in the 2.5 to 4.5. So it's pretty much guaranteed that that peak at 4 ppm must refer to this carbon. So that's this peak here. This peak must refer to this carbon. So what do I know about this carbon?
CH. There's two H's on it, and then it's attached to another C.
All right, now this is something I think that you guys, it wasn't clear to me that you guys had quite worked this out. So by working away from the oxygen, we know for sure that this is a CH2 group over here. Good. And doing a little more, can we figure anything out from the splitting of these hydrogens?
Yeah, it's a triplet, so it must be next to two other hydrogens. So the group next to it is a CH2 as well.
So notice how I'm working away from this oxygen, figuring out more and more definite stuff. Splitting is sometimes not helpful because sometimes the splitting is hard to interpret, but I think this is pretty clear splitting. I think it's pretty clear that this is a triplet. Okay, good. So we've gotten that far. So now, which peak in the Proton NMR does this refer to?
Which peak?
Now, so we now know that this carbon here refers to these hydrogens.
So it would have to be the second to the left.
It'd have to be these, right? Because these are the only other 2H. By the way, one thing you should be doing is labeling these as you go so you know which ones are done. So I might label these are peak A, and then these are A. Unfortunately, I can't write on this document here, but this would be peak A, and I've assigned A. And then I could say this could be peak B, and I'm assigning B here. That way you keep track of what you've gotten rid of and what you haven't. So so we know that that is this peak here, and it's kind of in the right region. It's further now to the right than the previous one. Now, what about this splitting? What does this splitting look like to you?
That splitting looks like
a quartet.
A quartet.
So it has to be
next to 3.
Yeah.
Now, so how many hydrogens should be on this carbon?
3.
No. That should be next. That should have 1 hydrogen.
Because there's already 2 over here.
Yeah.
Now, I don't want to emphasize that too much, though, because this splitting is not as clear to me that this is a quartet. It's probably a quartet. It's a little harder to see. Also, when you have non-equivalent carbons on both sides, the splitting is less reliable. These 2 carbons are not equivalent, so the splitting is a little less reliable. So that might make us guess that this is a CH, but I might want some extra confirmation for that. Okay, but anyway, at least we can get this far, working away from the oxygen. How about, and then what else can we do? Something else that jumps out at me. Obviously, this is an interesting peak here. What can we interpret about this? Maybe it would be good to work away in this direction. So which peak do you think refers to this carbon?
That's it.
Wait, which carbon?
Or that one there.
I don't.
Which peak do you think refers to this carbon?
Oh,
The one at 2?
Yeah, the 3H.
How do you know? Well, first of all, it's the furthest to the left of the peaks we have left, right? This is very close to the carbonyl and the oxygen, so it should be pulled to the left. So that would make us think that this is this too. So then we could put 3 hydrogens here. Does the splitting work if we put the 3 hydrogens here?
Yeah. Because it's a singlet and it's adjacent to a carbon with no hydrogens on it.
That's right. This is something that really should have jumped out at us here. When we see singlets are very helpful because there's not that many ways to get a singlet. When you saw this was a singlet, that should have been a strong clue that this methyl group was attached to the carbonyl. If you see what I'm saying? Because how else could it be a singlet? When you see that this is a singlet, that should be a strong clue that this is attached to the carbonyl, because otherwise it would be very difficult to end up with a singlet. So I don't think that was something that we were getting in our earlier pictures. That's important here. So there's a couple different ways to see that. So we can tell that this is this peak because it's farther to the left, and also it's a singlet, which would make us think it's attached to the carbonyl. All right, so now we're in pretty good shape. So we know this peak here was these two hydrogens, and this peak was these two hydrogens. And now you should probably be able to figure out what's left, because we have the two methyl groups. And the splitting here is a doublet. So they should be connected to a CH. I think that part you had already kind of figured out on your own. You had figured out that these were two methyl groups connected to a CH group. So I think now we can put the pieces together and say this is a CH, CH3, and this is another CH3, and we're done. Okay, so you guys were getting close. You were kind of dancing around this. You were trying a bunch of different possibilities, but none quite looked like this. I don't know. I don't think you ever tried putting this the key was that you were never putting this methyl group directly on the carbonyl. You were making this carbon chain too long. You were putting one CH2 group on the left and the other CH2 group on the right. So one key here is to really put this methyl group here. Okay, so the key thing here is to come up with some methods here that you can use yourself. So obviously one thing that it was very important here to see that this was an ester by using the detailed information from your IR table. But the other thing I did here that I think made this easier, do you see what I mean when I said I worked outward from the functional group? I started by saying that I know this is the functional group, and then I said which peak refers to this carbon. And that was actually pretty obvious. It had to be this peak so that it could be pulled so far to the left. And you can also ask which is this carbon. And then we could do even more because this had nice splitting. I think this is one problem. I don't think you were getting your two CH2 groups connected to each other. But if you work outwards, it's pretty clear that they're connected to each other because this has very nice splitting. This triplet has nice splitting that lets us work out this. And the other thing that you weren't quite using is that because this is a nice singlet, it's probably connected to the carbonyl on this side, and also because it's pulled to the left. So at the end of that session, you were trying to do something good. You were trying to look at each peak and write down everything you knew about it. But the reason I interrupted you is that can be kind of confusing. People usually work better if they're actually constructing the molecule by working outwards from the functional group. So that technique that I used here would be useful to you guys to actually center on the ester and then try to work outwards from it, identifying which peak over here refers to that. And it's very helpful to know that you want to use the peaks that are further to the left. Those are closer to the functional group. Does that make sense?
Yeah.
Yes? Okay. Let me also put this here now. Where would you expect these hydrogens to absorb?
Around.
Could you repeat that? The connection was bad?
Around 4.
So this would be the 2.5 to 4 that we were talking about before, right? I guess the point I'm making is I think you guys would have done better if you had used these ideas a little bit more in this last example. Whatever is on the carbon that's connected to the electronegative element is in this 2.5 to 4.5 region. I find that people have a hard time identifying these sometimes. They get these confused with each other. So I just wanted to do a little exercise on that. So this would be around the 2.5 to 4.5 region. And then where would we expect these hydrogens to absorb?
Those hydrogens, 1.5 to 2.5.
And how about hydrogens here?
Those would be like 0.9.
Actually, wouldn't they be the same as this?
No, they're equivalent. 1.5.
And how about around here?
Well, they're not exactly equivalent, but yeah.
0.9.
Or basically 0 to 1.5. They would be like these, right? So I just wanted to do a little exercise on identifying these three types of hydrogens. the ones that are closest to the electronegative element a little bit further and a little bit further. Because I think that's difficult for students oftentimes. So then where would these hydrogens be?
Those are like 2.5 to 4.5.
And how about these?
1.5 to 2.5.
And how about these?
0 to 1.5.
Good. So that's an important exercise. How about these?
1.5 to 2.5.
Hold on.
Is an alcohol the same?
So,
Yeah,
so
it's
the
just an
carbon is
electronegative
connected to the.
Yeah, I think it's 1.5 to 2.5.
And this?
Yeah, that's right.
That's
That-
2.5 to 4.5.
Yeah, that one hydrogen's gonna have 2.5 to 4.5.
Good. How about this?
That's gonna be like between 2 and 5.
That's right. This is the alcohol hydrogen, so it's in a pretty broad region. It's likely to be broad. Notice it doesn't follow this pattern. How about this hydrogen?
That's because
1.5 to 2.5.
And this?
0 to 1.5,
And this?
as well as the do it.
And this will probably be even further to the left than this. So I think this is a real helpful exercise. Now, you don't want to take this too literally. There are exceptions where things can be outside of these ranges, but these are good rules of thumb to try to use on these types of problems. Okay. So my main advice to you that would have helped you here would be to start with the ester and try working away from the ester and assigning the peaks as we go away, if that makes any sense. Does that make sense? Does that seem like a method you guys could have used? All right. Why don't we do one more problem? Why don't you, let's do compound 7 and then call it a day, if that's okay with you guys. So
yeah, that's
why don't
fine.
you maximize your drawing window again?
So just ignore the impurities.
Okay.
Compounds.
And the compound here is C4H5N.
That's 11 minus 5, which is 6 over 2, which is 3. You got 3 degrees of one saturation.
Yeah. Do we see
That's
peak?
It says impurity, but yeah.
No, look here. For an imine, we get a peak about 1660,
Mm-hmm.
and we have a peak at 1645.
Yeah, okay.
Oh no, I think that's an imine because it says conjugation lowers frequency. So C, the 1C is around 1600, and then this is just a little bit stronger than C to the 1C. So we have an imine.
1645. So that deals with 2 degrees of no, 1 degree of unsaturation there.
Yes. So these are all of our C's. Actually, no, we don't know if these are C's.
I mean, they would have to be C's, right? I mean,
Could this be an H?
you know, that's yeah, perhaps maybe. All right. So let's just keep going.
Any of them could be. Plus, we don't have any methyl groups.
We don't have any singlets either. So,
with doublets. Let's look at the doublets.
okay, so it's going to be peaks A, B, C, and D. That peak is at what? That peak is like 6? Like 5 point,
That tells
5 point, that's 5.8.
5.8. So that just looks like an alkene strat. An alkene.
Alkene?
Yeah.
Well, which is consistent with the one that we have there.
So you think that's the C? I do think to 1H though. No, I'm
Yeah.
doublets.
I'm going to give you guys a hint on this one. Where do triple bonds absorb in the IR?
Just below 2200.
Yeah.
Oh. Lovely.
Is that 2200 right there?
Yeah. It's not like the radio, like just.
One,
I think
two, yeah.
He would have meant to go to an alkene.
Yeah. All right. So that looks like a just above. So nitrile.
Leave an alkene somewhere.
No, it looks like a nitrile. Well, yeah, maybe an alkene somewhere as well, but this looks like a nitrile. Just above 2200.
Above 2200.
Yeah.
Because if it's an alkene, it would be just below 2200. So that's 2 of our degrees of unsaturation, and we have 1 more.
But we only have one end though. So is it the nitrile or is it
No.
the
I mean, we
amine?
just determined that it was a nitrile because it's just above 2200, and this peak is actually we can't really tell.
No, just yet. All right. So let's look at the peaks that we have.
No, it looked like it is just above 2200.
Yeah. No. Yeah. It definitely is just
I'm
above
pretty sure
2200.
it's a nitrile.
Yeah, but the thing is that we also have a sharp absorption at 1645. So it could be an imine.
Or an alkene. Let's
Or an
look at the
alkene. It
numbers.
might be an alkene then. What was alkene say?
Just about 1600. And then this is stronger. It's kind of vague. What, maybe his chart?
3.1.
Steve, does your chart say anything a little bit less vague about the frequency for the stress for the imine?
I thought you were using the same chart as me. But anyway, my chart has both alkenes and imines around 1660.
We can't decide if this should be an alkyne or an imine. If the nitrogen should be a nitrile or an imine.
Well, if it's an alkene and a nitrile, that cleans up our degrees of unsaturations.
I mean, it could be an.
Because that's 2 degrees of unsaturation.
Oh yeah.
1 degree of unsaturation. Yeah.
I mean, it could also be an alkyne and an imine might be the same.
Well, alkyne and imine as well. That's right. But let's look at the.
So go back. Remember when we started, I made a little table of some distinctive absorptions. Did I make a note there about alkenes? What's the best way to decide if you have an alkene?
4.5 to 6 on the NMR, and yeah, we have 5.8, 5.4, and 5.3.
So we have an alkene, and we have a nitrile group.
Good.
So each of these H's have to be in different environments because it's like 5.8, 5.4, 5.3. So that's consistent
And
with.
the H's on an alkene are going to be around 4.5 to 6. So we can be pretty sure. I would say that this 2H peak, I mean, that's just after 3, so it's probably not the 2H's on our alkene. So,
Well, essentially 3 H's are different. Okay.
From the nitrile. So we use 2 bonds coming off from the C of nitrile. And then they're either H's or C's. I mean, we know we have 1 C. And then this H decided it's an H or a C. We don't know. No, it's an H. But the N.
5. 1, 2, 3, 4, 5.
No, this N doesn't have an H. Do you know? How do you know that these are H's?
Well, just filling in.
What can?
So if this is in a different environment, this is in a different environment, and this is in a different environment. Each of these are in different environments because like this is like connected to a carbon with a double bond, and this is connected to this cis, and this is connected to this trans. So like each of these H's are different on the double bond, so that will correspond with the 3 different H's between 6 and 4.5. The D is at 3, so and that's a peak of what, 2? That's a 2 hydrogen peak. So that's going to be on.
How do you know that the alkene is here rather than? Because in the.
Because then that's the only way to get 3
alkene.
different H's between 4.5. If you made the alkene between 2 things, you'll only get 2 H's.
And we don't have any methyl groups.
Yeah. So to get the 2 H's at three is the struggle right now.
And he said that those numbers aren't definite.
Okay. So they kind of just fall there. They're like next to the well, if this H is a 2.5, the H that's only seen next to this could be like closest to 3, maybe. All right.
Well, that's
It
our final
matches,
answer
yeah.
for now.
Done?
Yeah.
Okay. All right, so let's talk about this a little. Obviously, we want to focus on the methods here. So first of all, how do we know when there's an alkene?
The obvious way is for hydrogens to be between 4.5 and 6 on the proton.
That's right. And notice that's pretty much guaranteed because there's almost nothing else that would ever absorb there. So that's a very reliable absorption. If you have things in the 4.5 to 6 region, that almost always means an alkene. So that should have been one of the very first things that we gravitated towards on this problem. Noticing that 4.5 to 6 absorptions, we should have been noticing there had to be an alkene in this compound early on in our work. By the way, what's the definition of an alkene?
Definition of an alkene, 2 carbons connected by a sigma bond and a pi bond.
So it's got to be 2 carbons connected by a double bond, right? Yeah. So if you have something in the 4.5 to 6 region, could that represent an imine?
No,
No, and
because
imine is not an alkene. I just mentioning that because at one moment there it sounded like you guys thought that it could be either an imine or an alkene. But 4.5 to 6 is only an alkene. It's not any old double bond. It has to be an alkene double bond. And there was other reasons you were thinking of imines too, but I just wanted to clear that up. 4.5 to 6 is not imines. It's alkenes. All right, now next, how can you detect triple bonds?
you can detect triple bonds by like um, degrees of uncertainty. Not uncertainty and
No,
like
I think you said
unsaturation of
that
like
in the IR.
2. And then like in the IR spectrum, there's sharp peaks at 2200.
That's very
And then
helpful.
also-
So I'm going to go back to my screen now. You can take another look at my screen to review this. So this is stuff that we talked about at the beginning today. Remember we said alkenes are detected from the proton NMR at 4.5 to 6. And we said alkynes are around 2000 to 2200. Your table is a little bit more precise than that. I should have done a better job here. Instead of just saying, I left out nitrogens because nitrogens oftentimes don't come up very much. But anyway, I should have just said here triple bonds. Or maybe I'll say alkenes or nitriles. Alkynes or nitriles, triple bonds. Alkynes or nitriles. I think this is a pretty reliable absorption. I just looked at the first 6 problems. And if you look at the first 6 problems, none of them have any absorptions around 2200. So, so it is pretty distinctive when you see an absorption around 2200. That's a very strong clue for a triple bond. So that's an important thing to add to your toolkit for that. So IR is especially helpful. So that would have been very helpful to you on this problem to figure out that there's an alkene and a nitrile. It's obvious there's an alkene because of the 4.5 to 6 absorptions. And if you notice the 2000 to 2200, then we can see that there's also a nitrile as well. Because there's a nitrogen, we should be checking if there's a nitrile, and then we can confirm that. I think one reason why it would be difficult to notice that is I noticed that in this spectrum, most of the peaks are numbered, are labeled with actual numbers. This one was easy to ignore because it didn't get a label. But even though it didn't get a label, that didn't mean it wasn't helpful. It still was helpful to pay attention to it. So how would we do this structure here? You guys came up with the right answer. You might have overcomplicated it a little bit. So when there's an alkene, start by focusing your picture on the alkene, like this. Now, some of these are carbons and some are hydrogens. How many of these attachments are hydrogens?
3.
That's obvious, right? That's obvious from our proton NMR spectrum. From this spectrum, we know there's 1, 2, 3 alkene hydrogens. So we can go right ahead and say hydrogen, hydrogen, hydrogen. And we also know there's a nitrile.
Can you repeat why it's obvious?
Sure. So if you take a look at this spectrum, would you agree with me that this is an alkene hydrogen? Because it's in the 4.5 to 6 region.
Oh, so just all of those hydrogens in that region.
And there's 3 of them, yeah.
You know it because of the region.
Yeah, so how many hydrogens are in the 4.5 to 6 region?
3.
That's why it's obvious. So it sounded to me like you guys were overcomplicating that step. You came up with the right answer, but you were maybe trying to look at the splitting or count how many equivalent hydrogens there are. You weren't. You could have used the integration more. The integration is a very helpful piece of information here. So in fact, notice that in general, it's always easy to see how many alkene hydrogens there are. It's always easy to figure out how many alkene hydrogens there are. Just count how many hydrogens are in the 4.5 to 6 region. So that's one thing we can do. And we also know that there's a nitrile here. And there's only one more carbon. Well, I know this is not the nitrile, right? Because then there wouldn't be room for this carbon.
Right.
So it's got to be like this. This is the answer you guys came up with, but it sounded like you were overcomplicating things. So I just wanted to show a shorter approach to it. We know that there's 3 hydrogens here because of 3 alkene regions. We know there's a nitrile, and we know the nitrile isn't directly connected to the alkene because then there wouldn't be room for the 4th carbon. So that's the whole picture right there. Now, you guys were a little worried that this was not absorbing in the right region. So now what region would you predict that it would absorb in?
Like around
4.5 to or 4.
well,
Well, according to your chart.
like the carbon next to
4.5 to 6.
I was thinking, no, that's not directly connected to an alkene though. It's connected to an alkene by a carbon. I was gonna say 2.5 because it's like connected to a double bond.
No, we shouldn't.
It's connected to the carbon, which is connected to a double bond. So I was gonna say like 2.5 ish.
Okay.
I guess it in 2.5 and 4.
First of all, based on this nitrogen, what region would we predict it would be in?
Based on the nitrogen on.
Well, that counts in the electronegative element. So you would think it's between 1.5 and 2.5.
Right.
If there were any hydrogens on this carbon, you might expect them to be, well, so anyway, using this rule that we talked about earlier, it's like these types of hydrogens. It's on the carbon that's connected to the carbon that's connected to the electronegative element. So we would expect this to be in the 1.5 to 2.5 region because the nitrogen's not on this carbon, it's on the adjacent carbon. Now, how about because of this alkene group, this is something that we haven't really talked about, but if you look at the little table here, would you agree that it's like this hydrogen?
Yeah.
It's not an alkene hydrogen, it's a hydrogen, it's what's called an allylic hydrogen. Have you ever heard of the term allylic? Well, anyway, it's the hydrogen on a carbon that's connected to the alkene carbon. So that would also predict 1.5 to 2.5, right? Does that make sense?
Mm-hmm.
Yeah. We haven't talked about that before, but that's a useful thing to know. Now, it's a little bit outside that range. It's actually about 3.1. But the point is, the point is that the nitrogen pulls this to the left, and the alkene also pulls it to the left. Because there's both of them, that explains why it's actually a little bit to the left of this region. It's getting pulled by both of these, so it's not too surprising that that method didn't work, because the method would be would apply if it was next to only one of them. Since it's next to two of them, it's not too surprising that it got pulled out of this range. Actually, it's still a little surprising to me. I wouldn't have predicted it would get pulled this far to the left, but we can kind of see what's happening here. The other thing is, we know for sure this is the only possible picture, right? We know for sure there's 3 alkene hydrogens, and we know that there's a nitrile, so what else could it be? This is the only possibility. So even if we are a little surprised by the chemical shift here, we have to accept this is all it can. This is as close as it can be. And we can kind of explain why it's outside of this region because there's 2 things pulling it to the left: the nitrogen on its right and the alkene to its left.
Sorry, how would we explain the doublet? Is that a doublet? Sorry.
Yeah, that is a doublet.
On the CH2, is it because it's well, I guess it's like 2 bonds away from that H over there.
Actually, it works out just like we would have expected. I think this is adjacent to 1 hydrogen, so you would expect a doublet.
Right. Okay, that's fine then.
All right. This splitting is a little harder to explain. You shouldn't worry too much about the splitting in alkenes. Alkene splitting is difficult. These 2 hydrogens are not equivalent to each other because one of them is cis to the nitrile and one is trans. So technically this hydrogen is getting split by this hydrogen and maybe also this hydrogen too. So the splitting in an alkene can be difficult to interpret. So fortunately we didn't really need the splitting, but splitting in an alkene can be difficult to interpret because you can be split by the hydrogen on the same carbon as you and 1 carbon away. Because of the cis-trans relationships. But fortunately here we didn't really need splitting to figure out the molecule. We could figure everything out just from the integration. Okay, so this is the first time we did an alkene. So I just wanted to remind you, here's the technique for an alkene. You're more likely to see that than a nitrile. You know, it's easy to see when there's an alkene because you'll see a peak in the 4.5 to 6 region. So you immediately write this down. And then it's easy to tell how many hydrogens there are on the alkene. by looking at the integration. So then you put however many hydrogens there are, and then whatever else is probably going to be a carbon, and then you can work away from that. So that's a good technique. That's the technique of working away from the functional group that we talked about before. Okay, so to wrap up, I think we've seen how some of these information here can be helpful to you. It's important to be able to recognize. You were asking whether you should memorize this. Maybe it is worth memorizing a lot of this, just so it's easier to access this. It's easy to see when there's an alkene because of these peaks. Triple bonds are easy to detect because of these. Benzene is easy to detect because of this peak. Alcohols are pretty obvious here. Carbonyls are pretty clear. And we saw that if you get a very detailed table like we saw, you can actually tell what type of carbonyl it is, whether it's an ester or an amide or whatever, if you have more information. Carboxylic acids are easy to detect because of this aldehydes. We focus on this. Ethers are harder. Ethers are harder to detect, but you're usually going to have something that looks kind of like this. One thing that we focused on was figuring out the functional group and then working away from the functional group. We did a couple examples of that. Okay, by the way, I should say, I think you guys have already learned, you guys did pretty well. These are hard problems. You guys didn't really start needing help from me until the last couple of problems. All the first ones you were figuring out on your own, which is good. Most people find this material very difficult, so you guys have made a lot of progress on this already. That's excellent. Unfortunately, the problems can be very difficult. So I would recommend going back and redoing these questions that we just did. Even the ones that you got right, it would be helpful to redo them, because most of them I think I was able to point out some ways that you might have been more efficient. So it might be good to redo those. But obviously you should redo the questions that you had trouble with as well, to make sure that you can actually get those right now. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.